Okay, so thank you, Yang Yang, for the introduction. Thank you to Yang Yang and Rongjie for organizing what sounds like an exciting seminar series. I'm really happy to be here. Let me go ahead and virtually let me go ahead and share the screen, and we can get started. All right, Yang Yang, do the slides show up well?
It's not the full screen. Can you show the full screen?
Okay, let's make that full screen.
Yes. Now it's
Okay.
yeah, now it's great.
Okay, so this is it. Okay, great. Um, so again, thank you. It's a pleasure to be here. Thanks everyone for coming to the talk. So what I'm going to do today is to give a kind of glossy and a little bit high-level overview of some adventures and misadventures that my students and I have had over the past few years around this area of non-convex optimization. Um, I'm going to show you what I personally find to be some very beautiful phenomena. Also, will make some attempts to make some sense of these phenomena mathematically. We'll see that we only succeed to some extent. So there are a lot of sort of exciting things that we don't understand and open problems. But that's the goal of the talk. We're a relatively small group, maybe 30 or so. So please feel free as I go to ask questions if anything is unclear, or if you just have a question. It would be fun to have a little bit of back and forth, even in this format. Before I get started, I'd like to thank a few people. So this is joint work with a bunch of folks. When I get into theory, the main results are joint with Yuqian Zhang, Qing Chu, and Ju Sun. We'll also show some experiments, and that involves a much larger group of people who we'll thank as we go. So I guess for this group in this seminar, I don't have to tell you that optimization is important. I don't have to tell you what an increasingly prominent role optimization is playing in industry, in the daily life, across our society, right? Whether it's in machine learning, where we're fitting gigantic models to gigantic data sets, whether it's in imaging, where an increasingly standard part of an imaging pipeline is to take measurements from some device and then solve an optimization problem that converts them into a picture. Under the hood, we're solving optimization problems. And because the field of optimization has been so successful, we're solving optimization problems that increasingly matter for people's day-to-day lives, right? And in a lot of these contexts, whether it's learning for autonomy, whether it's sensing for medical imaging, we really care about the quality of the solution that we get. In learning, maybe we care about our ability to generalize from a small data set, or ability to be robust to perturbations of the input data. In the context of sensing, it's very simple. We care that we reconstruct the correct picture, right? If I'm going to try to figure out what's going on inside my body for medical diagnosis, I really want the image that I reconstruct to be the right one. So we care about optimization, and we care about optimization as a device for getting correct answers. Okay. So let's see. I just lost control of the slides with it. There we go. Okay, so I don't need to tell you what optimization looks like. We have an objective function, f of x. We try to make it small. I probably also don't need to tell you that there are some optimization problems for which we can do this, and there are others for which we really can't. Right? In particular, if I look at the objective function on the left, this function is nice, bowl-shaped, right? By using local information, I'm going to be able to take actions that take me towards the global minimizer. And so local information, typically this means gradients and Hessians, right? The slope and the curvature of the function. Okay, so at left, if I take steps based on gradient and curvature and I organize this properly, I'm going to pretty rapidly ski down to the bottom. I'm going to get the correct answer. And again, going back to the application context, I'd argue that in a lot of scenarios, that's what we really care about, right? This is in contrast, and this is where I think the title of this seminar is interesting. This is in contrast with some classical applications of optimization, right? If you think about a logistics problem or some sort of a portfolio picking problem, well, you want to know that you're doing as well as possible, but locally improving your situation is very meaningful, right? If I improve my situation in that kind of a context, it means maybe I'm making more money or I'm using my resources more efficiently. Here, we don't just care about improving the objective function, we actually care about what we reconstruct. We care about the model or the image that we find. And so we kind of have a higher burden. We really want to find the bottom. We want to find the global minimizer or a global minimizer. Okay, and of course we all know that sometimes we can do this, as is the case at left, and other times it's challenging, right? Other times it may be NP hard to find a global minimizer. And one device that has been very useful for optimizers and also for users of optimization, such as myself, to think about this gap between what we can do and what we can't do is the notion of convexity, right? If we think about convex optimization problems, minimizing a convex function over a convex set, these are well structured such that the kind of local decisions that I was describing can generally be guaranteed to find you a global optimum. And so classically in application areas, in signal processing, in machine learning, if you find a convex formulation, you're golden, right? You know that that's something that you can solve. And in general, many convex problems are solvable in polynomial time. So, that's great. And because the class of convex functions and convex optimization problems is such a model for how to do this kind of work, right? It comes with well-structured algorithms with great performance guarantees. The class of functions is well-structured. There are composition rules and tools for identifying them. It's really, really tempting to sort of think of the world in terms of convex and non-convex, right? And the challenge with that is twofold. First is that convex is a well-structured thing. Non-convex is the complement of a well-structured thing. So on the right-hand side of the slide, a lot of wild things can happen. So that's the first problem. Second problem is that many of the optimization problems that we would really like to solve, problems showing up in signal processing, data science, naturally pose as non-convex problems. So unfortunately, for better or worse, usually we're over on the right-hand side here. Okay, and if we take a kind of classical viewpoint where we care about broad classes of problems and we care about worst-case performance guarantees, then in some sense this means that we're in trouble, right? Non-convex optimization, like optimization in general, is NP hard. And there are very basic reasons for that, right? We all know that it's easy to generate non-convex functions with spurious local minimizers. So a first obvious geometric obstruction to efficient optimization is bad local minima, right? NP hard to find a global optimum. Also, interestingly, and for myself, as not an optimizer by training, I found this very interesting when I learned it. In general, not only is it NP hard to find the global minimum, it's also NP hard even to find a local minimum, in the sense that it's not difficult to make objective functions that, although they lack spurious local minimizers, are so flat that it's hard to find a direction of descent. In particular, in the example at right on this slide, the objective function is so flat that in order to descend, I would need to look at fourth derivatives or higher. So this really rapidly gets me into hard problems in the algebra of tensors. Okay, so these are our two geometric obstructions to optimization in general, and non-convex optimization in particular. So what I'd like to do with the next part of the talk is actually start by showing you an experiment. So I think there are probably a fair number of students in the seminar. When I was a student, I was a very eager student, and I very eagerly indoctrinated myself into this way of seeing the world. There's convex, which we can solve, and then there's everything else. And it was a little bit disreputable to go over there. So I want to show you an experiment that started to change my view on this a little bit, and then that'll kind of be a lead into the second part of the talk, where we try to zero in on a few non-convex problems that we can solve. So this is a talk for optimization in imaging. So this experiment kind of comes from image processing. It's representative to some extent of what folks were doing maybe about 10 years ago. In the modern context, you can kind of see this as a baby version of representation learning. So in this experiment, I'm going to take this picture, this image, and I'm going to try to learn a concise representation for that image. And the way I'm going to do it is I'll take the picture, I'll chunk it up into patches, and then I'm going to put those patches as columns of a big matrix, which I'll call Y. So here, little y is an n by p matrix. Little n is the number of pixels in a patch. P is the number of patches in the image as a whole. Okay, so just a way of converting a picture to a data matrix. And now, what I'm going to try to do is I'm going to look for a concise encoding of that data matrix. In particular, I'm going to look for a factorization. I'm going to try to write y is q times x, where x is sparse. And there are a lot of reasons for preferring sparsity in image processing. There's a deep literature on this, but our reasoning here is simply that we want a concise approximation. So if x has only a few non-zeros, then this is relatively small. Okay, so in this expression, y is q times x is sparse. And both q and x are unknown. I'm going to try to determine them from data. Here, this operation that I'm describing is sometimes referred to as dictionary learning. The q can be considered a dictionary in the sense that in this expression, y is q times x, the columns of y, these individual patches, are going to be written as sparse linear combinations of the columns of q. So I can think of the columns of q as a basis for representing this particular family of signals. Okay. Any question about the setup here?
So John,
patches overlapping?
Okay. Are the patches overlapping? Okay, so that's a good question. That's often a question that you ask around these types of models. So in the experiment that I'm going to show you, the patches are not overlapping. You can make them overlapping. Also, if you really care about doing this for image approximation, it's probably a good idea to make the model convolutional. We'll talk about that a little bit later, but I just thought I would throw that in there since, if you're asking about overlapping versus non-overlapping, you probably appreciate that there's an issue with deciding to chunk up the image in a particular way. The clean way to get around this is to make the dictionary convolutional. We'll see a little bit of this later in the talk.
Just clarify. So
sure, please.
Usually P is much bigger than N, right?
Yes.
Well, it may not be, but then Q here, you mean Q is like an orthogonal matrix? Q
okay.
Is in,
good.
Oh,
no. Okay, yeah. So I was, so maybe I neglected to talk about Q. Right. So there are different types of dictionary learning problems. You can try to learn a square dictionary, a complete dictionary, which just means that you're learning a basis for representing these patches. Or you can try to learn an overcomplete dictionary. And in general, as you might expect, the overcomplete dictionary has more representation power. As a consequence, you need more data, and it's a little bit trickier to compute with, right? You have to think about, basis pursuit or matching pursuit to find the representations. But it has advantages in terms of representation, in particular if you want to sparsify a diverse data set. Here, I'm going to make the restriction that the dictionary is square, and I'm actually going to ask it to be an orthogonal matrix. So as you mentioned, this is a major restriction. The reason why it's sort of morally okay here is that here I'm learning from a single symbol. So, in general, the optimal size of your dictionary is going to depend on the data that you want to learn over. If you want to learn over a large and diverse data set, you need an overcomplete representation. Here we're going to use a complete representation because we're only learning from a single picture.
Okay.
And actually, that's not as, it's not as ridiculous as one might think. I mean, here we're just doing this for illustration purposes, not really to advocate it as a procedure, but there's been a fair amount of investigation in image processing and in medical imaging. And there are a lot of situations where you can get a fair amount of the way by using a complete dictionary. Also, some of the learning problems, as we'll see, get a lot nicer. So we're going to do a complete dictionary here, but we can talk about overcomplete later.
Okay, thank you.
All right, cool. Thank you, everybody, for the questions. So this is our problem. I'm going to try to factor y as q times x, where q, as we mentioned, is an orthogonal matrix. And x is as sparse as possible. And there's a sort of time-honored way of doing this in signal processing and statistics. I solve a big optimization problem that trades off between fidelity to the observed data. Here, this is the Frobenius norm squared of y minus qx, and the sparsity of my representation, complexity of my representation, here penalized through the L1 norm. Okay, so big optimization problem. Again, this is a constrained optimization problem. I'm asking Q to reside on the orthogonal group, and I'm minimizing something that looks like a lasso cost. Okay. Now, one immediate thing to note about this optimization problem is that if I'm trying to solve for both Q and X, then this is a non-convex problem, right? Although the objective function is convex in X with Q fixed, once I have both Q and X as unknowns, they interact in a bilinear fashion. The objective is non-convex. The constraint set is actually also non-convex, right? I'm asking Q to reside on the orthogonal group. Perhaps a more fundamental source of non-convexity in this problem is the symmetry of the objective function. And this is something that we're going to see in this problem and also in another number of other problems as we go. That if I think about my dictionary Q, its columns, as representing a collection of building blocks that I'm going to snap together to approximate the given image, the representation power of that dictionary doesn't change if I permute its columns, right? In particular, if I reorder the dictionary and I make the same reordering to the coefficients, I get a representation that is just as accurate and just as sparse, right? So this problem exhibits a permutation symmetry. And so we sort of expect that if you found one good solution, then there are a combinatorially large number of other equally good solutions in the space. So for that reason, we expect that this problem is non-convex, right? Simply because it has a large number of disjoint global optimizers. Okay. All All right. So what I'm going to show you in this experiment is what happens if we take this non-convex optimization problem and we throw a very naive method at it. So I'm not going to do anything fancy. I'm just going to pick a starting dictionary Q at random. And then it turns out, because of the properties of the objective function, I can actually easily solve for Q with X fixed, solve for X with Q fixed. So I'm just going to pick a starting point at random, and I'm going to bounce back and forth until I'm happy with the result. We're going to take a look at what that looks like. Okay, so I'm going to stop sharing my slides, and we're actually going to share MATLAB. And I apologize, this is always going to lead to fumbles, but I really like to show the experiment because it helps drive home that what we're going to talk about in the talk are actually real phenomena. You know, maybe we can't capture all of them mathematically, but these are things that happen. Okay, so I'm going to go ahead and do what I just described. So I'm going to pick a random starting point. I've loaded an image. It's not the fish. It's actually this picture of the Golden Gate Bridge. What's plotted in the graph is the objective function as a function of iteration. So we iterate for a while, bouncing back and forth between the Q and the X. Eventually, we reach a representation. The one that we reach is being plotted right now. It actually doesn't look like that much, sort of spots and bars. This is typical if you try to learn representations with a single layer. Maybe some of the bars reflect some of the linear structure in the picture. Now, what's being plotted in red is what happens if I try to solve the same problem from a new random starting point. Right? So again, it bounces around and eventually settles on the same objective function. Now in yellow, again, from a new random starting point. And now again, from a new random starting point. And so you can see if you look at these curves, if you're really an optimizer, when you look at these curves, you'll notice that there's something a little bit funny in the geometry of this problem, right? Because it's not just sort of smooth descent to the finish. You know, things can slow down and speed up. On the other hand, the really salient aspect of this graph is the endpoint, right? Although the path you take to get there may vary a little bit, the final objective value seems to be the same in every run of the algorithm. So you can see again, we converge to the same objective value. And if you were to look at the dictionary that we learn each time, the dictionary that we learn each time would actually be the same as well up to this fundamental sign permutation symmetry. So this doesn't quite get all the way to demonstrating experimentally that we're finding the global optimum, because you need math for that. Who knows? Maybe there's some smaller point somewhere else in the space. But it's really suggestive, right? Because what it says is that, at least for this problem, initialization doesn't matter. Even though I used a very dumb algorithm and just sort of bounced back and forth until convergence, I always get the same quality of solution, and I always, in the dictionary, get essentially the same dictionary. And this is not special to this picture. You can try it with other pictures. I think our code is available online, so you can play with it and try to break it. If you set the lambda really, really small, you can make it break. But for reasonable settings of the lambda, it seems to happen. So I'll go back to the slides. Sorry. Okay, let me get the slides back. While I'm doing that, any questions about the experiment?
So what method are you using in the experiment? It's just gradient descent?
Okay, thanks. So this is an alternating directions method that holds q fixed and solves for x, and then holds x fixed and solves for q. There's some special structure in this problem that makes each of those steps efficient. In particular, this problem of finding the best orthobasis for a given data set reduces to what's known as an orthogonal Procrustes problem. So you can basically solve that with an SVD. The problem of solving for x given q is a lasso problem, but the particular lasso problem that we run into here is efficiently solved with one iteration of soft thresholding. So it happens that this particular formulation is really nicely amenable to this sort of alternating directions. But I think that the result doesn't depend too much on the method, in the sense that the result is that somehow initialization doesn't matter, right? We always find solutions at the same quality. And my experience is that if you were to, for example, smooth out L1 and then do gradient descent, you would also see that maybe it would be a little bit less efficient. Other things as well. Does that help?
Can I ask a question?
Yeah, please.
Okay, so here you have q a square, right?
Yes.
So I'm just curious, if you were to relax this a bit, right, and instead of having q square, you have q rectangular, so it's not a full basis for Rn, right? Then
Right.
Do you run into more difficulty? Just because there is kind of, I mean, not for this problem, but within deep learning, right? You have a lot of these papers by like Dauphin and Kromanska that show that these lost landscapes have tons of saddle points, but it's just that once you over-parameterize your network, right, you essentially never hit them during training. So I'm wondering if you see that same kind of behavior here.
Yeah, okay. So first of all, thanks. That's a really good question, and it's a really good piece of context. Yeah, so I agree. So I like the question, and I think that we have to be a little bit careful. Just for everyone in the room, we have to be a little bit careful, because thinking about over-parameterization in deep learning, where I make my network wider, maybe even so wide that I have more neurons than data points, is a little bit different than over-parameterization in dictionary learning, where I sort of make my dictionary really big. As you mentioned, when you make your dictionary big, in this setting, things get a little bit rougher, in the sense that when you think about sparse approximation problems, even if you know Q, if Q is overcomplete, that sparse approximation problem is only solvable under conditions. So already when you go to the overcomplete case, even without having to learn the dictionary, things are a little bit rougher. If you have to learn the dictionary as well, then you need more stringent conditions on the data. So the math that I'm going to show you in this talk is for the complete case, and then also for some related problems in deconvolution and in imaging. There are some extensions of these results to the overcomplete case, but I completely agree with you. It's trickier. There's more that could go wrong. Now, you also mentioned this phenomenon of flat saddles in deep learning, and I think that's a really good point. None of what we're going to show you in this talk pertains directly to deep networks, although I think the perspective at least has a little bit of value in thinking about them. The perspective that we're going to take in this talk is basically to try to understand how the symmetry structure of the optimization problem affects the geometry of the objective function. And in some relatively simple problems, it's possible to actually argue that the only interesting thing is symmetry. In essence, all of the non-convexity can be understood through the lens of symmetry, and you can guarantee global optima. We saw that experimentally just now. Now, when you talk about flat saddles in deep learning, you can also see this through a symmetry lens in the sense that when you start putting layers on top of each other, you have compound symmetries because now you have a symmetry between each layer, and you can sort of argue that this compound effect creates in some parts of the space these flat directions that may be hard to escape. If you're interested more in connections to deep learning, we do have a recent paper that doesn't really go through the symmetry properties as much, but sort of tries to think in this over-parameterized regime using tools from measure concentration and low-dimensional structure. And that's probably the easiest place to make progress in that problem area. Thinking about the network as a whole is really hard. Okay, does that help?
Yeah, thank you so much.
Sure, that's great. I can see we're going a little bit slowly, but I appreciate all of the questions. I think this is fun and clarifying. Okay, so if you really have this worst case picture in mind, then some of the phenomena that we just saw might be a little bit surprising, right? From a worst case perspective, maybe this shouldn't happen. Or maybe there's some special property of this particular objective function that makes it better than the worst case. Okay, and so over maybe the past 5 years or so, the field as a whole has been out to figure out what's going on, not just in this problem, but in other non-convex problems that seem to be amenable to efficient methods. And I don't think that we have all of the answers at this point, far from it. We just mentioned deep learning, and that's one area where I think we're really still looking for answers as a field. But one thing that does come through from the few problems that we do understand is this really critical role of symmetry in shaping the optimization landscape. That in some of these highly symmetric problems, there's this nice global geometry, and as a result, you get global solutions. So these are just a few examples from my students and from the field that are looking into these phenomena, mostly in simple model problems. So these are problems like dictionary learning, deconvolution, low rank recovery, phase recovery, so on and so forth. So what I'd like to do during the next part of the talk, and I can see it's going to be rather brief because we've already done 35 minutes, but is to take you on a quick tour through two of these problems. We're going to see how this plays out from a theoretical perspective in dictionary learning and in sparse blind deconvolution. And then we'll sort of come back to the big picture. Now, before we talk about these non-convex optimization problems that we may or may not be able to solve, it's worth starting with the one that we can solve, because this does have something useful to teach us. So if you do numerical work, there's one non-convex optimization problem that you solve maybe almost every day. And that's the problem of minimizing a quadratic form over the sphere. Right? And this is non-convex, even if the matrix A is semi-definite, this is non-convex because the constraint is non-convex. The reason that this problem is important, of course, is because the critical points of this problem are eigenvectors, right? If I look for a point where the gradient is normal to the constraint set, that's going to give me that AX is proportional to X. So all of the critical points of a quadratic form over the sphere are eigenvectors of the matrix. And they're graded by eigenvalue. So local minimizers are eigenvector corresponding to the smallest or most negative eigenvalue. Local maximizers are the biggest eigenvalue. Everything in between is a saddle point. Okay. And this one is fun if you're a student because, frankly, this literature is a little bit horrendous to engage with. A lot of the papers are very technical and a little bit brittle. You feel like we still need better tools. Some of the papers are 50 or 100 pages long, but this is one that you can do on a piece of paper right now. You can do it in the next 5 minutes. If you have the right notion of a gradient over the sphere, a Hessian over the sphere, then you can investigate. And what you'll find is that the only local minimizer for this problem is the eigenvector that corresponds to the smallest eigenvalue. Well, and of course, that comes as itself and it's negative. And everything else has a direction of negative curvature. So in some sense, in this particular problem, we've avoided our two worst case obstructions that we started the talk with, right? For this problem, you can go home and show that there are no spurious local minimizers, and every saddle point has negative curvature, so you won't get stuck. Okay, and so we're going to just abstract away these properties a little bit. We're going to say that from the perspective of an optimization method, we're happy with an objective function if at every point that's not close to a global minimizer, one of these two things is happening, right? Either there's a direction of descent, there's strong gradient, or there's a direction of strict negative curvature. And I've put it on the slide in a little bit more formal manner. If you sort of put parameters on all of this, then you can use those parameters to analyze the convergence of methods and, you know, get bounds on the number of iterations to well approximate a minimizer, so on and so forth. But at a high level, the structure that we're looking for is either strong gradient or strong negative curvature. And it's going to turn out, when you start analyzing the kind of problems that I described earlier mathematically, negative curvature is going to be the key. In convex analysis, positive curvature is the key. Here, negative curvature is the key. And the reason is simply that negative curvature is what gives you symmetry breaking. If I have two equivalent minimizers, then you better hope that in between the objective function is shaped like so that I'm going to be able to fall off to one side or the other. So a lot of the analysis really tries to zero in on directions of negative curvature. Okay, so let's just sketch a little bit how such an analysis would go. The details, again, are kind of awful, so I'm not going to give you all of the details, but just describe it at a high level. So as a device for doing theory, I'm going to posit a model for the data. I'm going to imagine that there's a true dictionary out there in the world. There's like a best dictionary that we're trying to find, and that the data really are generated as that dictionary times a sparse coefficient matrix. Again, I'm going to make two assumptions here. One of them is kind of major and structural, and the other is a technical convenience for doing math. It's basically a concession to the limitations of our reasoning abilities. The major structural concession is, as we discussed before, I'm going to make the dictionary Q0 square and invertible. The technical convenience is that I'm going to assume that the coefficients x0 are sparse and chosen at random. So each one is on with some probability theta, and when it's on, in the model, it's a Gaussian random variable. Of course, this can be relaxed to some extent. But the big restriction here is that we're thinking about square dictionaries. Now, the reason that restriction helps us to be able to take some steps towards doing analysis is that for square dictionaries, I can move easily between the row space and the column space. If Q0 has full rank, then the row space of the data matrix Y is the same as the row space of the coefficient matrix x0. And so I can think about the problem of finding a sparse x0 not as looking for sparse columns, but as looking for sparse rows. So this is kind of some theoretical trickery, right? Like if I'm in this scenario, then I can reduce the problem, and this way I can think in terms of the rows or the columns. Reason that thinking in terms of the rows is powerful is that it gives you a kind of geometric perspective on the problem, where I can think about the problem as trying to find sparse rows in a linear subspace that I know ahead of time. So the geometric problem could be considered as I'm handed a linear subspace, which is the row space of Y. That subspace contains n sparse vectors. Those are the rows of x0. Now I want to find those. If I find those, then I know x0 up to a permutation of those rows, and hence I can also find q0 up to a permutation of those, up to a permutation of the columns. Okay, so this suggests an algorithm that is not the best possible, but actually works and can be analyzed, which is I'm going to go ahead and look for those sparse rows. So if I try to just find one sparse row, what I'm going to do is I'm going to solve an optimization problem where I minimize the L1 norm of Q transpose Y. Here, Q is a vector of coefficients. I'm looking for a linear combination of the rows of Y that is as sparse as possible. And because I want to make sure that I find a true row, not just zero, I'm going to constrain the scale of Q. I'm going to ask the L2 norm of Q to be equal to 1. So in terms of the optimization, in terms of the model that we set up, this is going to turn out to corresponding to finding the dictionary atoms one at a time. And the optimal Q here is actually going to correspond to one of the rows of the dictionary Q0. So I'm sort of finding or one of the columns of the dictionary Q0, sorry. So I'm finding columns one at a time, rows one at a time. Again, doing them all together is better computationally, but this is the thing that we can guarantee, and also the proofs sort of shed some light on the geometry as a whole, even when you try to do the whole matrix. So we're going to go with this for now. So we're minimizing L1 norm of Q transpose Y, subject to norm of Q22 is equal to 1. Okay, and it turns out in our model, the objective function is random. This is what the population objective function looks like. This is its expectation with respect to the data. And you can see here, this objective function is kind of like an L1 norm over a sphere, right? The constraint set is a sphere. We started with an orthogonal group, which corresponded to the dictionary as a whole. Now we've reduced to a sphere, which corresponds to a single column. And you can see, even with this reduction, there are multiple equally good solutions. These are the red points. These correspond to different columns of the true dictionary and their negatives. So, you know, they're sort of spread about on the sphere. If you look at this picture carefully, you'll also notice that there are a tremendously large number of other critical points. There are local maximizers in these yellow regions, and there are saddle points in the kind of green valleys in between. So if you imagine this picture in high dimensions, if you believe that it carries over to high dimensions, then in high dimensions, you should expect that there are exponentially many critical points, right? Critical points seem to happen roughly at balanced superpositions of these symmetric solutions, right? In between the two red points, there, which are minimizers, there's a saddle point. In between the three red points, which are minimizers, in the middle, there's a maximizer. So spurious critical points seem to happen at symmetric superpositions of true solutions. And as we'll see, at those points, there's a direction of strict negative curvature. So if this is really the picture, then actually we're in very good shape for finding the red points. We may not know which one we find ahead of time. That depends on where we start. But we know that we're going to find at least one of them, because those are the only minimizers and everything else is well structured. This is just showing the same thing in coordinates. this makes it a little bit easier to see the geometry. So here what I've done is I've projected everything onto the equatorial plane, and then I plot the objective function as a height over that plane. You can see that instead of acting like a convex function, this function is actually kind of acting like a symmetrization of a concave function, right? It's like we've taken one thing and now we stamped it down here, 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 glued them together. And again, you can imagine that this is a landscape that you can navigate without having to worry too much about getting stuck. Okay, now to show this mathematically, this is this is not everything, right? These are just pictures. So what we have to do is to dig in and spend some amount of work analyzing this expectation. Also, the objective function, is taken over a finite data set. We need to account for that effect using concentration of measure. In particular, you want gradients and Hessians to be uniformly close to their population versions. And so, if that's the case, right, if you have enough data, then you get from something that might be a little bit rough in a small sample setting to something that has this nice geometry to where you're going to be able to find correct answers. Okay, and this is a thing that one can prove. So this theorem is only a sketch, but what you can prove is that if the problem is more than a little bit sparse, in particular if that theta is bounded below a constant, say a third, and you've seen enough data, in particular a number of samples which is polynomial in dimension n, then with high probability, every local minimizer produces a close approximation of the truth. And the function has this auxiliary property that at every bad point, every point that's away from a minimizer, there's either a strong gradient or a direction of negative curvature. And the way that the analysis goes is to really think about the symmetries of this problem and think about symmetry breaking directions as negative curvature directions. So most of the work is sort of showing that in between two good solutions, you don't get stuck. Okay, so this is the picture, or maybe this is the picture, and this is a slightly more formal version of the same result. Any questions here, either about the picture or what one can prove about it? Or about the formulation?
Yeah, maybe we can leave the questions finally.
Yeah, sure. At this point, we only have 10 more minutes. Yeah, sounds good. Okay, so it happens that the theoretical algorithm can also be made practical, so you can recover reasonable dictionaries in this way. Honestly, I think the thing that's most interesting here to me is not so much the theorem, although that's important to make things rigorous and to argue that they sort of still happen in high dimensions, but is really the picture, right? Is that in this particular problem, if you simplify things enough, if you strip away enough detail, then what you're really confronted with is the symmetry structure of the problem. And fortunately, that plays in your favor. Although you can't guarantee which minimizer you find, you can guarantee that you'll find one of them. Okay, so this is a first example of this phenomenon from a slightly more theoretical perspective. In the brief time remaining, I'd like to give just one more example. This is going to be at kind of lightning speed. This is in sparse blind deconvolution. This is motivated by problems in imaging, in particular in electron microscopy. I have neither the time nor the expertise to tell you in full detail what one is after here. But for us as sort of optimizers, as imaging people, as data scientists, the data analysis problem that I get from this device is actually a fairly fundamental one. So what this device produces, and this is collaboration with Abhay Pasupathy, he's from physics in Columbia, is a data cube. So I have 3 dimensions. 2 of them are spatial, 1 is voltage. This is produced by scanning a sample. Typically, this is some putative high temperature superconductor, some material whose physics is not known ahead of time, and I want to interrogate the physics. Okay, so to interrogate the physics of the material, what I'm going to do is I'm going to take this cube, again, space cross voltage, so sort of space cross energy, which tells me something about the quantum mechanical properties of the material. And I'm going to look for recurring motifs in this cube. So it turns out wherever something interesting is happening in your sample, electrons scatter, they produce a little characteristic pattern. That characteristic pattern depends on the state of matter of the material and some other things that may not be known ahead of time. And so the basic problem here is finding little patterns in data. I have data that are a superposition of motifs that occur at different spatial locations. I want to find those motifs. And here, I'm motivating it from my own experience, which is in a collaboration in microscopy. But this problem of finding basic motifs in data is a fundamental one. This shows up in neuroscience, neural spike sorting. The motif is the spike pattern of a neuron. It shows up in astronomy and in other imaging problems. It shows up in other microscopy modalities. So, this particular problem of motif finding is an important one. So how do we convert motif finding to an optimization problem? Well, the natural way, which has been practiced in all of those areas, is to write down a model for our data, which is a convolution of 2 terms. One is the motif. That's what I've labeled A here in this slide. And the other is a sparse activation map that tells you where the motif is happening in the sample. So what this model says is my data was generated by taking my basic motif and then stamping it down here, 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 here. And everywhere I'm going to stamp it down, I put a spike. So in this model Y, my observation is A, the motif, involved with X, the spike train. Okay, so again, this is kind of an imaging seminar. There are a lot of models for deconvolution out there, especially in the theoretical literature. We like to refer to this as a short and sparse model, in the sense that usually the motif is relatively small compared to the sample as a whole. It's short, and the activation map acts as sparse. And those 2 pieces of structure are important because this is an ill-posed problem in general. Now, again, it's really easy to write down an optimization formulation for solving this problem. If I want to find the motifs, what I'm going to do is I'm going to take Y and I'm going to try to solve for A and X by minimizing a combination of data fidelity and sparsity. The only thing that's interesting in the formulation is here, the way I've set things up, I have to make a constraint on A to break the scale ambiguity between A and X, right? Otherwise, the L1 norm becomes unhappy, X becomes really small, and everything breaks. So here, for that purpose, I'm going to constrain A to have unit L2 norm. I'm again going to constrain it to live on the sphere. This is the only thing that's sort of interesting about this formulation. Everything else is what every one of us on the call will do. The interesting thing about that sphere constraint actually comes from the geometry, in the sense that when you really dig into the math, what you'll find is that this negative curvature, which breaks symmetry, comes from a combination of the curvature of the objective function and the curvature of the constraint manifold. And so both of those are important in combining to create this effect. So once we get to doing analysis, this sphere constraint is going to be really important. It's going to play a fundamental role. But otherwise, this is pretty much what one would do. Now, here again, we have a symmetry structure, but the symmetry structure is a little bit different from dictionary learning. Instead of a permutation symmetry, what I have here is a signed shift symmetry. in the sense that if I move the motif to the left and I move the spike to the right, they still convolve to produce the same signal. So instead of expecting local minimizers to be permutations of the truth, here I might expect local minimizers to be shifts or sign shifts of the truth. Okay, and it turns out if you throw reasonable methods at this one, you can find such things. I won't belabor this too much because we've already, it works. I've heard that it's helpful for our colleagues. It sort of gives clearer results than what one was doing before. I think the general interest here is what does this tell us about non-convex optimization, right? What picture can we take away? So for theoretical purposes, again, we can zero in on a simple model problem. Here, our simple model problem is going to be in one dimension. We're going to make some technical assumptions on that simple model problem. Again, we're going to assume that our spikes are chosen at random. That's sort of a technical convenience. And we're going to assume that our A is nice. And here, what nice means is that its shifts are not too close together. So it's shift incoherent. That's going to be helpful in sort of sorting out which shift of the truth we're converging to. And our theoretical results articulate trade-offs between these two parameters. So as the coherence of A gets worse, then you need to have a sparser sample to find the correct answer. This is sort of what one would anticipate. Okay, this is just illustrating, at left I have a dense and incoherent problem. At right, I have a sparse and coherent problem. And the theory sort of gives you a trade-off between these two things. Now, like before, these are hard problems. We're still developing the tools, so we're going to hack a little bit to get something that we can analyze. Here, we hack a little bit on the objective function, so we manipulate the objective function a bit. Once we make that manipulation, the geometry that comes through is pretty nice. So here is the objective function in the vicinity of a single shift, right? So you can see this nice convex geometry. Here is in the vicinity of two shifts. You can again see nice convex geometry around each with negative curvature in between. Here is for multiple shifts. You get this sort of egg carton structure where the different shifts of the truth are minimizers. And in between, there's negative curvature that's going to drop you into one of the basins or the other. Now, in contrast to what we showed for dictionary learning, we don't have the technology right now to prove that this holds over the whole sphere, but we can prove that it holds over the important part of the sphere, which is the part of the sphere that is near superpositions of ground truth signals. And so you sort of get an analysis that's around a union of subspaces, again, corresponding to these different shifts of the truth. What you can prove is that with high probability on this set, the geometry is nice. And based on that, you can provably recover those ground truth motifs. So, finally you get to a guaranteed method. Okay, so I went lightning fast through that. I think following Yang Yang's suggestion, I will leave questions for the end, but we can come back if there are any questions on this. I'll say that if you're interested in theoretical analysis of deconvolution, then what's sort of different or interesting here is the short and sparse model. The theoretical literature uses a bunch of different random models, many of which don't have the same or as many symmetries, kind of act more like matrix recovery problems. Also, I'll say that this issue about the domain of optimization is interesting. So it turns out if you choose the right domain of optimization, then without very many fancy image priors, just get the optimization correct in the spirit of this seminar, you can actually do quite competitive deep blurring. So this is blind image deep blurring, comparing a simple method for optimization over the sphere with fancier methods that assume more about the statistics of natural images, but maybe are formulated over different spaces. Okay, and these benefits carry over to other problems as well. So I think what I'd like to do is just close. So I'm sorry for going slightly over time. I'd like to just close with a little bit of the bigger picture. So we saw in two examples how symmetry can shape the geometry of optimization. What sort of comes out of this literature as a whole is the beginning of a kind of classification by example, right? We don't have general theorems, but we can divide the problems up by example. And one nice cut is around the symmetry group. In particular, is it an orthogonal or special orthogonal group? Do you have continuous symmetry? Then you get problems that act kind of like the generalized phase recovery problem. That's one I didn't have a chance to talk about. These problems are often amenable to convex relaxation, but can be solved more efficiently by non-convex methods. And they have this kind of beautiful continuous symmetry structure. A lot of the open challenges are around discrete symmetries. We mentioned dictionary learning and deconvolution. Tensor decomposition acts like this. Certain phase retrieval problems may act like this. We mentioned nonlinear neural networks as an important open problem earlier. So a lot of the interesting action and a lot of the need for better tools is around discrete symmetries. And I'll say that for most of these problems, we don't have good convex relaxations. So these are the problems where we really, really need to be non-convex, and we need better understanding of what's going on. Okay, then a final issue that I don't have a great deal of time to talk about is maybe the interest to Yang and to a lot of people in the room is what are the implications for methods? And a high level is that any reasonable method works once you have good geometry, but there is an interesting cut around the behavior of randomly initialized gradient descent. Randomly initialized gradient descent is efficient in general for what are known as strict saddle functions, functions where every saddle point has a direction of strict negative curvature in a certain quantitative sense. So randomly initialized gradient descent still inefficient in the worst case. You need to use higher order information or inject some noise or something, but it generally works in practice. And so, why is that? What additional geometric structure causes that to be the case? And again, there's a lot of reason to believe that the reason for that is, at least in these simple problems, is the symmetries and the negative curvature structure. That where in the worst case, saddle points feed into saddle points, feed into saddle points in an adversarial fashion. In the natural case, or in this highly symmetric case, there's a global negative curvature structure to where escaping up here helps you to escape down here. Okay, and so there's a little bit of theory around this, but there's a lot more that needs to be understood. Okay, so with that, I will thank you for coming to the talk, for your attention and your questions. I'll leave you with this as a general picture. Thanks to all of my collaborators. Here are a few references. And if we have time, I'll be happy to take more questions. So thank you, everyone.
Thank you, John. Thank you for the nice talk.
Thanks.
Yeah, maybe we can ask 1 or 2 quick questions, because we are already running the time.
Yeah, sorry, we started slow and got fast.
Yeah, we asked several questions during the talk.
Yeah, but I'm happy to take any more if there's time and folks have them.
Yeah, John, if I may, thanks so much for this very interesting talk. So I really enjoy this interaction between the symmetry and the negative curvature. Is that fair to say for generally objective function, as long as you have a discretized group symmetry? you can imply negative curvature, or you have to assume there's a negative curvature. It's the
Yeah, good, right. So yeah, is there a strict implication there? That's an excellent question. So the answer is, in general, no. There's no strict implication, in the sense that it's, well, let me think carefully. So I think in general, it's possible to make examples where this fails. It's definitely easy to make examples of symmetric functions that have spurious local minimizers. You might, I sort of agree that you might be able to, if you partition by symmetry, you might be able to derive some implications on curvature at the boundary, although I think it doesn't, there's nothing in symmetry that forces it to be negative instead of positive. So it's a good question. So I think the answer is nothing in general. But on the other hand, it seems like any naturally occurring problem that we write down exhibits some of this phenomenon. And so there's a feeling like the counterexamples must be artificial in some sense, and so you'd really like to be able to capture that somehow. So I think it's a great question. I don't know how to do it except case by case. We have a lot of sort of creative ideas for general approaches to solving multiple problems, rather than, we don't want to write 50-page paper for every problem. We want to understand general principles. Thus far, it's been a little bit hard to get anything to really work in general, but I think it's a good direction. And yeah, it's intriguing.
So is a spherical constraint very critical here? Because it's like a curvature between the objective function and the curvature of the constraint domain, right? Is that the important component of the landscape?
It is, in the sense that if you change the constraint, then it sort of changes the curvature of the landscape. I didn't. So if we had another half an hour, there's a simple version of the dictionary learning problem that I could walk you through, where you reduce it even more, and you can sort of see. So the dictionary learning problem, the objective is an L1 norm. The L1 norm is piecewise linear. The curvature of that function over the sphere is almost entirely due to the sphere itself, because the objective is piecewise linear. Also, a non-negative linear function over the sphere, like if I restrict to the area where it's non-negative, on that set, that linear function is concave. You can sort of visualize it just by seeing how it cuts the level sets. And so you can sort of see, with not too much work, that the intersection between the curvature of the sphere and the objective function creates this piecewise concave structure that we saw in the graph. It's just, if you want to get that to come through in math in a more general model, then you have to work really hard. But point is, it's a good question, and the curvature of the constraint set does matter. Maybe you could replace the sphere with an ellipsoid and things would still work. That seems possible, or maybe with some other set that interacts appropriately. But yeah, both matter in shaping the landscape.
Okay, thanks.
Sure, thanks.
More questions?
Excuse me. Yeah, I have one question.
Sure.
Yeah, very good talk. Give me very many good intuitions. I have one question, that if we like the non-convex problem that has a strong gradient, or the negative curvature, but if the optimization problem is not like this, how can we
What can we do?
Change the object? Is there some some intuition how to change the object function or the constraint so that our object function, our problem can become like this?
Good. Yeah, that's a great question. And again, I think it's one that's a little bit hard to answer in general. I think both your question and the previous one is sort of saying, okay, this is an interesting phenomenon, but what's a general toolkit? Now, I can give you a couple of intuitions here.
Yeah, right.
One is that choosing an appropriate constraint set can make a difference. It seems like spheres and orthogonal groups tend to play nicely. You might attribute that to the curvature structure of those manifolds. So if you have, for example, if you have a bilinear inverse problem, really think about putting one of the factors on the sphere, because that does tend to make things better. Another is that in the examples that we've looked at here, the objective function sometimes has this kind of piecewise linear structure, and that's a nice structure for interacting with the sphere. Although the phenomenon is not sort of restricted to there, I can show you examples that are not that. But I would say a degree of freedom that you have is by putting some of the factors on a sphere or an orthogonal group or a Stiefel manifold. This actually does seem to help, and sometimes seems to get rid of local minima.
Okay, great.
But another thing to say is that, like, sometimes you encounter a problem. So there are a couple of things that can happen. Sometimes you encounter a problem and you try to be clever and it hurts you. This was actually the case for dictionary learning, right? So we started out trying to be clever, and then we got a lot of mileage by instead just going back to the thing that was working for people in practice. So, sometimes the simple methods are good. I know I wasted a lot of time banging my head against symmetry breaking in dictionary learning, and it turns out you don't need it. So that's one. The other is that sometimes you encounter a problem where you try the tricks that I just described and it doesn't work, right? So a great example of this is, like, it's a bad idea to waste your, well, anyway, I don't want to say specific things, but there are certain problems that I've wasted my time on that are sort of suspected to be hard, where you felt like maybe if I can just change the geometry, then it'll turn out not to be hard. And, sometimes I think it's just in the problem and the data that you're not going to be able to solve it tractably.
Right.
So that's some general experience there.
Yeah, very helpful. Thank you.
Okay, great.
Okay, I guess if you still have questions, you can email to John after this talk, because we're running out of the time. It's too late, I think. And thank you again, John, for this very interesting talk.
Okay, well, thank you everyone for coming, and thank you Yang and Rangjie for hosting. Thanks.
Yeah, thank you.
Thanks, John.
All right, thank you.
Yeah, take care. Bye.
Bye.
Bye.